All right, guys, welcome back. We're going to now continue looking at force normal examples. So we've already posted videos on number 1, 2, 3, and now we want to look at number 4 here, what we're doing if it's being pulled at an angle on an incline. So be sure you go back and look at number 3, as it's important to understand how number 3 works so that we can get number 4. All right, so number 4 is determining the force normal. So here's one of our things we're looking for. And we're also looking for the force applied, okay, with respect to the horizontal. If a 70 kilogram box is being pulled by a force of 80 newtons at an angle of 60 degrees. So draw the force diagram to support your answer, okay? So this is a little bit different than the box is being pulled at an angle instead of sitting on a incline. All right, so start off with, we just have a box here, and this box is being pulled at an angle of 60 degrees, and the box has a mass of 70 kilograms, okay? And so all right, there's that force again that we always have to label first that we can't get away from, and that is the weight of the object. So the weight of the object is mass times gravity. So we could go ahead and solve that if we'd like to. 70 kilograms. Now be sure, kilograms is a mass. So anytime you see a kilogram, you know you're going to need to multiply that times 9.8. So 70 times 9.81, the weight of our object would be. Okay. So clear that out. 70 times 9.81, and we get 686.7. And that would be a Newton. So we had a few errors in that today. Remember, so kilogram is mass, and Newton is a force. That is our weight, and it is a force. All right. So what are the other forces that we have here? Well, we have the opposite of the weight, or the force normal. All right. So because this is on 0 degrees, I can start right off and say that the force normal equals the weight. But there's something going on with this 60 Newton force here that we need to take into consideration. And so think about what's happening here. If you're actually pulling this with 80 newtons, okay, and remember, force normal is this contact force between the table. Well, if you're pulling up at 60 degrees, you're actually decreasing the amount of contact. So the force normal is not going to completely equal the weight. It's going to be just a little bit less due to this contact right here, okay, becoming smaller. So this is our force normal. So if we remember our basic vectors, right, our 80 Newton has a force in the y and a force in the x. So you should remember from our basic component systems, right, how do you find f of y? So f of y is the sine of theta times the hypotenuse here, or the resultant. So it's going to be the sine of 60 degrees times 80. And that will be our f of y. So f of y equals. So we get our calculator out, and we solve that. Sorry. So clear all that out, and we go sine of 60. So 60 sine times, let's see, what else we got, times 80. And I'm getting 69.28. Okay. So get 69.28, and we'll just record that as 3. And that would be a Newton. Okay. All right. So now we need to find our f of x. So the y is the sine component. The x is the cosine component. So the cosine of 60 times 80. And we find the f of x. So we solve that out. Cosine of 60, and we plug all that in, cosine 60. And we get 40. All right. So now, we got all our parts. Now we're ready to solve this. So remember, when you have 0 degrees, the normal case is force normal equals the weight. But because I'm pulling up some, because this 80 newtons is pulling up, then there's some parts that are decreasing it. So the force normal is now equal to the weight minus the force in the y direction, which we've already solved for everything. So we could just plug this in now. So we'll come over and we'll say force normal equals the weight, which we know is 686.7, and that is a newton, minus the force in the y direction, which is opposite the weight. Notice how this vector is pointing up and this vector is pointing down, so they're opposite directions. And we know that to be 69.3 newtons, okay? So now we're ready to just get that answer. So force normal equals, so 686, all right, 686.7 minus 69.3, and I get, I got an error is actually what I got. Try that again, 686.7 minus 69.3 equals 617.4, and that would be a newton. So this orange vector here can now be labeled 617.4 newtons if we wanted to. That is the force normal. So we found the force normal, okay? Last thing we're looking for is the force applied. Well, you're pulling with 80, but the only applied force with the horizontal is the f of x. So this force applied, so force applied in the x direction is what we've already solved for, 40 newtons. And so that would be the final part to that problem, okay? All right, so now, if we look back at our last example where we had number 3. So number 3 was this example of an object on an incline, and we went over that you got your weight, force parallel, force perpendicular, and force normal. And then up here is our force friction. So we talked about all those. We got to take this example, combine with number 4, and solve number 5. Number 5's got a lot of little pieces together. It's a combination of several individual problems. Okay? So let's tackle number 5. All right? So again, we got a lot of different pieces to provide room so you can easily see. I'm actually going to work it on a second piece of paper once we get going. All right? So start off with, we want to determine the force normal. Okay? So force normal, question mark. And so I need to think about, is it 0 degrees or some angle? Because that changes my original idea, my thought process, how to solve this problem, okay? So let's keep that in mind. We'll come back and answer that. We also want to know what force is applied, okay? So force applied equals question mark, and force normal is question mark. So we have a 50 kilogram box being pulled by 50 Newton force at an angle of 30 and is sitting on an incline of 45. So we have a 45 degree incline, and sitting on this incline, we have a 45 degree incline. Sitting on that incline is a box, and that box is being pulled at 30 degrees. So if you imagine someone right here has this box, and they're pulling that box up at 30 degrees, okay? So now we have a combination. we have force normal being pulled at an angle of 30, but we also have it on an incline of 45. All right, so we need to add the mass of the box over here as a little note. And we go back to our problem quickly and we find that the mass of the box is 50 kilograms. Again, remind yourself when you see that kilogram that that's a mass, you'll need to multiply that by 9.8 to get the weight. So 50 kilograms is not the weight. Some problems will just give you the weight. For example, this says it's being pulled by 50 newtons. That's the force. We don't need to do anything special to that. It's already in newtons. But 50 kilograms, we got to do something to that to get it into newtons. All right, so I think we got all our givens and we're ready to go through the solution of this problem. So to start off with, it's on an incline. So it is some angle. So when force normal is on an angle, it's important that you know this. You'll have to just remember it. This is part of the things that you're trying to learn. Force normal, when on an angle, equals force perpendicular. So let's find force perpendicular. So start off with our free body diagram. What's the first force that we have? We can't get away from, and that is the weight of the object. So here's weight. All right, and we can label weight F of G or W. Okay, what does the weight equal? Weight equals mass times gravity. Here's our mass, 50, and gravity is 9.81. So we'll go ahead and label our weight. Go ahead and solve that. So 50 times 9.81, I get 490.5 newtons. So that's the weight of the object, okay? All right, now, so if this was horizontal, then we could just go right off and see that. All right, so let's continue to label our incline diagram that we've already worked on in earlier videos. So remember, some of the weight pulls the box down the ramp, and that is called force parallel. Some of the weight pulls the box into the ramp, and that is called force perpendicular. There's a force that's opposite force perpendicular. We know that to be force normal. So we know that force normal is equal to force perpendicular. So we definitely got to solve for force perpendicular. Now, one way to solve for force perpendicular is to remind yourself of the equation, or you could look back on your sheet and we go, oh, here's force perpendicular. We know that's the cosine component of the weight. So let's go ahead and solve for force perpendicular. All right, so force perpendicular down here is going to be the cosine component of the weight. Now, we're not using the 30, it's the cosine of the incline, the 45. And it's times the weight, which we already know is 490.5. So cosine of theta times the weight. So we took our weight and substituted it in. We took the angle of the incline, not the angle that he's pulling with, but the angle of the incline. So we'll solve that out. We'll get force perpendicular equals. So cosine of 45. All right. If we get this calculator running, we go 45 cosine times 490.5, and we get 346.8 newtons. And we'll just use one decimal. All right. So is that our force normal? Well, if it was only on an incline, it would be. But remember this problem we just worked a moment ago, right? Just a moment ago, we showed that if someone's pulling at an angle, that the force normal decreases a bit. So we have that same scenario here. So because this is being pulled, since it's on an incline, force normal is equal to force perpendicular. But because it's being pulled at an angle, force normal is going to decrease by some amount, by the amount he pulls up with. Okay? So when you pull an object like this character here is doing, when this character is pulling, some of his force is in the Y direction. We're running out of room to label that. Force, the Y direction. He's lifting it up. Some of that 50 pulls up, and some of that 50 pulls across. Some of that 50 is going right here. That we'll call X. Force X and force Y. So some of the 50 lifts it off the ramp a little bit. Right? What would happen if this 30 degrees got to 60, 70, 80, if it was all the way, right? He eventually is just picking it straight up off. So again, as you lift at some angle, you're decreasing the force normal by that amount. So you thought it was equal to force perpendicular, but now you realize that it's decreasing by F of Y. So if we take a moment here, maybe we can try to show this. Everything's getting on top of each other. So the force perpendicular and force of Y. Notice those are opposite each other. They're parallel and opposite. So I'm going to end up simply subtracting them. And what are they going to equal? Force normal. So you see that these three vectors, and I'm putting that circle around, are all in these parallel to each other, and we're just going to simply add and subtract them until we find the other one. So force normal is going to equal force perpendicular because it's on an incline, but we want to decrease it by force of Y because someone's pulling it up. So we've got to combine those. So how do we find F of Y? Well, we've done that enough over the past couple of weeks. You shouldn't have a problem with that. The Y component is the sine of theta times the resultant. Now this theta is not the incline. This theta is the angle at which the person's pulling with. So it's the sine of 30 times the resultant force, 50. So the force in the Y direction is sine 30 times 50. So we'll take a minute and solve that up. Okay. So clear our, see if we can get this, here we go. So we go 30 sine and times 50, and we get 25 newtons of force. So that's 25 newtons of force lifting up. So we're ready to finalize force normal. So force normal equals the force perpendicular, which is the cosine component of the weight, and we've already solved for that. So 346.8 minus F of Y, which is a component of the 50 newtons, the component at which he's pulling with. We found that to be 25. So force normal equals 0.81, 321.8 newtons. So there's our force normal. Okay, and again, remind yourself, what is force normal? It's this contact force between the ramp and the box. Because the box is on the incline and because he's pulling it at an angle, the contact force decreases. It's not equal to the weight anymore. It's a little bit less. So 321. Now remember, our other question that we will want to find is the force, excuse me, let's move that back up. We'll go back to our question. We want to find force normal. We got that. Now we want to find the force applied. So we know he's pulling with 50. So we know he's pulling with 50, but not all of his 50 is actually pulling it. Remember, it's got these components. Some parts of the 50 is lifting. Some parts of the 50 are pulling. So the force applied is going to equal the force in the x direction. Well, if y is the sine component, x is the cosine component. So the force applied is the f of x, or the cosine of the theta times the resultant. Now this theta is the angle he's pulling at, not the angle of the incline. but the angle he's pulling. So it's the cosine of 30 times 50. So f of x equals, and we'll get the calculator to solve that. So 30 cosine times 50 equals, and we get 43.3 newtons. So the force being applied is 43.3 newtons by the boy. Is there any other forces in that direction? Yes, force per parallel. So we got to take into consider this f of x and f of parallel, because remember, he's pulling up, but gravity is pulling it down. So how do we find force parallel? Okay, a lot of steps to this problem. Here's force parallel. Force parallel is the sine component. So we'll go down here. We'll find force parallel. We'll just squeeze it in this section right here. Force parallel is the sine of theta times the weight. Now this theta is the incline, because now remember, force parallel is dealing with this incline. So it's the sine of 45 times the weight, which we already solved earlier, 490.5. So force parallel, sine of 45 times 490 is going to be 346.8. Now we did get the same number for these, and that's just because we gave you a 45. So if you remind yourself, a 45-degree triangle has equal legs. So we should expect those to be equal, but that's not normally the case. Now, look at our diagram. If you're going down with 346.8 and you're going up, this little f of x right here, this little green vector is only 43. I mean, you're going down with 346, you're going up with 43. Force parallel, this is down. Force applied, this is the up. How much force is actually being applied? So the force applied down, okay, the force applied down the ramp equals gravity pulling it down, force parallel, minus the boy or person pulling the box up. Gravity pulling it down, the boy pulling it up, f of x. So we know the force parallel is 346.8. We know f of x is the 43.3. So the force applied down the ramp is whatever this here comes out to be, 346.8 minus 43.3, and I get 303.5 newtons, okay? So the force applied down is 303. Guys, these are multiple problems put together, and it's not as complicated as it seems, but you must practice it, and I would almost recommend just work the same problem several times till you get the hang of it. Then change the numbers around, okay? So if we take a moment before we shut down the video here. The other day we worked number 3. Number 3 is when it's on an angle, and I made a separate video about solving that as an angle individually. Number 4 is a box that's pulled at an angle. So this is on an incline and pulled at an angle. Number 5 is the combination of those two problems together. You have lots of little pieces, but it's only sine and cosine, and adding or subtracting. Okay? So I want you to work number 5, and I would encourage you, get you a scrap paper, rework number 5, and just practice working it. Practice making this diagram. Practice solving all the little pieces, force parallel, force perpendicular, force normal, the force in the y direction, the force in the x direction. Just practice solving those. Repeat this same problem several times until you get the hang of each little piece. And then when we change the numbers, you'll do better. All right, so at this point, though, after we've done these examples, you should be starting on additional practice calculating force normal. So start solving these problems, okay? So you see here, these are the very basics, all right? Now we got it pulled at an angle, like our example that we worked tonight. And then we got another one where a kid's pulling it at an angle. Okay, on the back, we got these here. Now we're starting to look at ramps down here at number 10 and so forth, okay? All right, so see if you can give these a try. Post your work, and I can look at it and send me questions, and we'll see if we can't get some good success, all right? So force normal on an incline being pulled by an object, or excuse me, being pulled by incline. All right, guys, good luck.